And there, that's everybody. All right, how's that for convenient? Good afternoon, everyone. Welcome back to geometry. We are rolling through our section on circles. And that was not everyone. Oh my gosh, I can't count. Denver, hello, welcome. Missed it. Maybe if I actually read with my eyeballs, I would have seen that. Okay. Anyways, back to geometry, circles, and all of their wonderful round circular features. Of course, now that I think about it, we're looking at a lot of features that also involve straight lines on top of circles, right? It's the intersection and the interaction between all of these things that gives rise to some fun stuff. So let's start with reviewing all the fun stuff from yesterday with our tangent properties. So here are my answers. Please take out your work from yesterday and check how you compare. And ask me any and all questions. What confuses you? Hey, wait a minute, why did you get that? Okay, 1 and 2, fairly straightforward. 3, part A is direct application of a radii are perpendicular to the tangent. That's it. But then it requires a little bit of thought around what you know of quadrilaterals to determine this must be a trapezoid. Since these are both perpendicular to the same line, we've got kind of a CIA, consecutive interior angles. 90 plus 90 is 180. They're supplementary. So these lines are parallel, and that's the only parallel thing, so you get the trapezoid from that. And then here is 4 and 5. Bring it on screen, as well as, we'll just bring up 6 there as well. Four, I would say what you should start with is finding the slope of this line segment first from 0, 0 to 3, 9, because you know as a radius it must be perpendicular to the tangent line. Perpendicular, opposite reciprocal slope, and that gives you the slope for the actual tangent and then point slope from there. Number 5 is a basic syllogism here. We know A has to be congruent to B, and B is congruent to C, and C is congruent to D, because each of those pairs does intersect the same circle. And so we can apply this is equal to that, and that equal to the third one, and to the fourth one, and so forth, right? To get A chained all the way to D. And number 6 is the difference between internal versus external tangency. Okay. Internally tangent, 2 circles that touch at one point, one inside the other, so you're going to subtract their radii, whereas externally touching outside, so you'd have to add up the radii there. Okay, remaining questions on that page? No? All right, then let's jump into today's feature presentation, arcs. Not just good for surviving floods, right? And before we can do anything with the arcs themselves, we must first look at what slices them up in the first place, right? Because an arc is a portion of the circle. So what caused us to start portioning? Well, usually the result of some kind of an angle intercepting the arc of the circle. And that could come out of the central angle here. Right? It's a central angle because its vertex is on the center of the circle. Or an inscribed angle. Inscribed means to be drawn inside of a circle with all of your points on the circle. So the inscribed angle also hits points A and C, just like this one, but its vertex is out on the circle itself, not in the center. Okay? So the difference is, compared to that intercepted arc, let's say for the sake of argument that was 70 degrees of arc there, then the central angle we know is equal to that 70 degrees, right? Their measurements are equal. But an inscribed angle, if this is 70 degrees of arc out here, this guy is definitely going to be less than that. And I could show you visually real quick. Oh, let me get my lines to actually make it a little bit bigger. Actually connect them there. If you were to take that central angle and move it on over without adjusting the size, notice it is definitely much bigger, right? Turns out it's exactly twice the size, which means the inscribed angle is half of the intercepted arc. Isn't that convenient? That would make this guy 35 degrees. That's really nice how it works out that way. You go from central angle to the arc, right? And those will match up one for one, which kind of makes sense. They both have to meet 360 degrees around for the full circle. But the inscribed angle is always going to be half of that. And we'll see maybe perhaps why it needs to be half in a moment. But that's it. If you can remember these two facts, central angle is equal and the inscribed angle is half of the arc, you'll be set. That is technically enough to answer the appropriate questions on our worksheet today. However, it's not always the most useful. There's a few consequences thereof, immediate results of applying this fact to some specific scenarios that give us some even more useful shortcuts. Okay? And that would be, what happens if you have more than one inscribed angle? Multiple inscribed angles going at the same arc. Let me draw an example here. On my inscribed angle, we could go over here. Call that point E. How about that guy? It still intercepts this same arc AC. No matter where I draw point E there, it's intercepting the same arc. It has to thus be half that arc, so it's also going to be 35 degrees, no matter where I put this. So all inscribed angles intercepting the same arc are congruent. Okay. And then next up, we have what happens if you inscribed an angle into only half a circle, a semicircle, right? Just a real quick sampling of one, let's say about there. And you would imagine we have the rest of the circle coming around like this, right? But only on half the circle. So the end points of our inscribed angle is something like that. And no matter where I draw this, those endpoints are going to be there. And thus you can imagine the intercepted arc of this inscribed angle is actually the other half of the circle. And if all of this, half a circle is 180 degrees of arc, then this would have to be half of that. So it's always going to end up 90 degrees, right? All angles inscribed in a semicircle must be right angles. I'll draw my little square in there. And that also gives us an idea of why it must be half in the first place, because that's as big as it can possibly go. Right? I can't, if I was to try to intercept an arc bigger than that, well, now I'd have to bend back around, and it wouldn't be. Well, I guess you could still draw one in, not covering the whole thing, right? You can see the limits on that, right? As we get smaller and smaller half of it, eventually you're just a line. Okay. Okay. Questions on those ideas? Geez, I'm getting a lot of emails today. What's up with that? Nothing in the morning, and then all of a sudden now, everybody's got to talk to me. No questions. Okay. Then, next up, when we're dealing with arcs, there are two ways to talk about and measure and compare arcs. And that is the arc measure itself versus, new today, is the arc length. Okay? And just as it sounds, the arc length, is measured in meters or inches or feet, etc. Any other unit you would use to measure length. Arc length is a length. You measure it exactly the same way. Whereas arc measure, as we've been using it, is in degrees or radians, okay? Just like an angle. So the arc measure is a direct correspondence with that central angle. It's measured the same way, same size, same units. Whereas arc length is a distance. In fact, let's write that down as well. An arc measure tells us how much turn you've done inside the circle, how much you have rotated around. Okay? Whereas the arc length tells us how much distance you'll have traveled, right? I go here and I work my way around the circle. Right? I've gone that much around, but how far did I go? How much ink did I have to expend in my, let's pretend I'm using a pen that lays ink down, right? How much time, if I'm drawing at the same rate, it takes longer and longer, the bigger the circle. I'm having to go farther around. That's the difference between arc length. It is bigger and bigger with a bigger and bigger circle, right? Because you have to go farther. It's small circle, small arc length, big circle, big arc length. Okay? In fact, I would summarize it thusly: the arc length is proportional to the arc measure and circle size, which we would usually indicate with the radius, right? So a larger arc measure, right, wider and wider opening of that central angle, you're taking more and more of the circle, of course the length goes up. And if the circle itself is bigger and bigger, the arc length gets bigger and bigger. It's length, it's more inches, it's farther, I'm running around a longer track. As an equation, that would be set up like this. Here's your proportion equation, arc length over circumference, right, is equivalent to the arc measure divided by the full circle, which we usually use 360 degrees to indicate. So either one of them represents a fraction of the circle. They both represent the same fraction. But it's which type of fraction are you talking about? Fraction of rotation or fraction of distance? And from this setup, this relationship, we can derive a simple equation, a formula, if you will, to find the arc length directly. You're simply going to take your arc measure, whatever it is in degrees, and divide by 360 degrees. If it was in radians, you divide by 2 pi radians, right, the full circle. And then take that fraction and multiply by the circumference of the circle, which we usually find by 2 pi times the radius, r. That's going to be our most common starting point, as we'll have the radius. Okay? We can indicate that. That is the circumference itself. So if you already have the circumference, of course, use that. If you have the radius, use that. If you have the diameter, remember the diameter is twice pi, or twice the radius, so only need to multiply by pi. And that'll get you your arc length. Any questions there? Okay. Giselle, if you need to go back for anything, you can immediately scrub through the video as soon as the live broadcast is stopped live. Okay. All right, then a few pointers on today's exercises. Up here we've got the first half dealing with the inscribed and central angles and maybe some other angles. We've got a tangent line thrown in there as well. Okay, these first 6 have to do with those angles. And the latter 6 have to do with the arc lengths. Okay, so we'll be finding arc lengths or solving from the arc lengths back and forth with that equation. Do notice, the directions say leave your answer in terms of pi. Do not plug in 3.14 into your calculator. Leave pi alone. Treat it exactly as you would some unknown variable. Just leave it as x, all right, in terms of x. So for example, if you were to set up the first one here, we want the length of arc AB. That would be this arc right here. Okay, so length of AB arc would be equal to its measure. We can see they give us its arc measure right there, 120 degrees out of 360. Multiply that by the circumference, 2 pi r. So 2 times pi times our radius right here is 6. Okay, so if you leave the pi, 2 times 6 is 12. 120 over 360, cross out the zeros, 12 out of 36. 36 is 3 times 12, so we have 1/3 times 12, which is 4, so you just get 4 pi. Oh, sorry, that's a little in the corner there. And that's it. That's how you'd leave your answer. You would just write it exactly as that, 4 pi. Okay, that's our answer left in terms of pi. That's also the exact form. Anytime you plug in a decimal for pi, it would be an approximation. Okay, final call for questions. None? All right, then I will leave the rest of them up to you. Let me know if you run into trouble. But we'll call the YouTube stream done here.